All right, I'll get started now. Thanks everybody for coming. My name is Dan Lawrence, and I'm going to be talking about, there we go. I'm going to be talking about how to make slightly more secure GitOps pipelines using Jenkins X. I'm going to introduce myself before I get into it. I'm an engineering manager at Google, and I've been working inside of Google Cloud for about 6 years now. I've been doing a bunch of container, Kubernetes, and Docker things lately, mostly focused on how to make developers' lives and jobs easier. I've been working with containers since about when Docker came off, or started to take off, about 4 or 5 years, which is like 50 years in DevOps terms. So it's been a while. Today, my team is responsible for a broad range of container tools, and we're currently working on things like Minikube and Scaffold to improve iterative Kubernetes development. Some tools for building containers inside of Kubernetes clusters like Canico, and then a bunch of other CI/CD related things more recently. So for the rest of this talk, I'm going to be talking about securing GitOps pipelines, specifically those created by Jenkins X as the main examples. There's a bunch of different flavors of GitOps, so I'm going to explain what the overall buzzword there kind of means, some of the different ways to set it up, and then we'll deep dive into exactly how Jenkins X uses and sets up GitOps. I'm going to explain some of the security trade-offs and both benefits and drawbacks you get from using GitOps versus something, a different type of CI/CD system, and then go into how to make them more secure. Part of that is going to be a little bit of a deep dive into the Grafeas and Kritis open source projects, which I'll be using to establish a sort of binary trust during these deployments. And then at the end, I'll give a quick intro to some of the other low-hanging fruit you can do to get a more secure cluster that I don't have time to cover today. So GitOps is a bit of a buzzword of a name. The term popped up a little over a year ago, but it's really a grouping of a bunch of concepts in CI/CD that have been around for probably longer than I've been in the space. But the overall idea of GitOps is to set up your build and delivery pipelines using a pattern where all of the changes to production happen first from a change to a source code repository. No developers or operators ever touch the production or staging environments. Instead, everybody triggers changes and rollouts by making changes to a code repo. And then there's that kind of GitOps magic loop on the right-hand side, which is a tool or process that's responsible for constantly reconciling the desired state, which lives in some kind of code or config repository, with the actual state, which is living in production. Doing changes and rollouts this way allow all of the production changes to go through your organization's standard source code review process. So you're changing production just like you're changing features in your code. This reconciliation loop on the right is a pretty common pattern in Kubernetes, which is why GitOps has started to take off recently. All changes to Kubernetes happen from changes to things that look like source code anyway. So this is kind of just letting it come full circle. We're also going to be talking about Jenkins X for all of this. Jenkins X is basically Jenkins, but with an X in front of it. We got this man to pose last night for this picture. Just kidding a little bit, but it's actually a pretty awesome tool from CloudBees to automate setting up a Jenkins-driven CI/CD environment based on GitOps inside of a Kubernetes cluster. You install it on your laptop, run a few commands, and then you have a whole working system out of the box. It sets up repositories for preview environments, deployment environments, staging, and all of that stuff, as well as automatic promotion between these environments, and then preview and development pods inside of the cluster as well. I'm not actually brave enough to do a live demo of Jenkins X, so I cheated a little bit and set up my cluster ahead of time. But this is what the repo structure and the cluster setup kind of looks like and how code flows between them. I'll jump out to the Blue Ocean UI in a second. But developers make changes to the code repo, which is basically one microservice. You also have a few of them in the same repo if you want to. Once that gets merged, it triggers a set of tests that run against a staging environment. Once all of those tests pass inside of a pull request on GitHub, Jenkins automatically merges that pull request, and then the GitOps magic applies those new configurations and binaries to production. The final step is a manual promotion to the production environment. You can also configure that hold flow to be automatic if you have enough tests and confidence in your process. If you're interested in more details and how Jenkins X works, there have been a bunch of really good talks on this, and I think there are a few more coming up, so definitely go to one of those. After I set up my cluster, I used a Golang HTTP quick start application that comes in one of the Jenkins X tutorials. It's a simple Go server that builds into a small Docker image and serves basic HTTP traffic. If I come over here, I can take a look. So here's the Blue Ocean UI you get out of the box. I can zoom in. This shows the environments I was talking about before. This pipeline is for building and merging changes to master from the HTTP app. Staging will run every time something gets merged to master. We can click into here and see the runs, some passes, some failures. And then promotion to production is manual. So you run a job locally or click in here to do the actual promotion. This is the commit history for the code repo itself. You make changes directly into here. You can change the source code, your Docker images, and each one of these, each one of these triggers a build and a rollout to master. That build, this is production. Let's jump over to staging. So you'll see there's a bunch of activity going on in here. All the pull requests are closed though. These are all opened on behalf of you by Jenkins X automatically. So every time something passes and gets merged to master, Jenkins X will create one of these, run all of the tests, and then merge it for you. And once this gets merged, it gets rolled out to the staging environment automatically. There's kind of robots reviewing and merging the code for you to make your job easier. Let's see if I can get back to the slides. Awesome. Yeah, so I'm going to talk about securing GitOps and some of the trade-offs involved. I've heard a joke a couple times before that the S in blockchain stands for security. GitOps actually has an S, which is pretty accurate because it's actually a pretty good starting point for a secure CI/CD system. Most of the main benefits from these GitOps systems are that all of the events occurring to production are triggered by events through a source code system. So you can go back and audit all of those later and see who changed something and why. Some of the other benefits are a greatly reduced attack surface on the cluster. Your developers don't have permission to get into the cluster. It's really just the GitOps agent doing all of these changes. So the cluster is a lot more locked down than you would have normally. One other disclaimer before we get into this, I don't really want to be making claims that something is secure or isn't secure. All the images have vulnerabilities, but they might not matter. Security isn't a Boolean, it's kind of a spectrum here. All these decisions you might make kind of affect a different set of trade-offs between your developer productivity, ease of debugging, and that kind of thing. So I'm really just focusing on some of the low-hanging fruit if you do decide you need to make your cluster a little bit more secure. So chain of trust is a pretty common metaphor when you're talking about security, especially in supply chain management. It's a pretty good metaphor because just like a chain, the security of your supply chain is as secure as the weakest link. It doesn't really matter how many times you apply patches to your production cluster every day to pick up CVEs if some intern set up a WordPress instance that nobody knows about and is serving traffic on some QA domain that nobody remembers. So the cluster and the pipeline are both as secure as the weakest link inside of them. We're going to start on the right here and talk about what containers are running in production and then move up to the rest of it. Some of these look pretty trivial, but when you start looking at Kubernetes and diving into the details, especially with Jenkins X and GitOps, there are a few nuances you might not realize at first. So that's where we're going to start. So this is a little bit of a quiz. Does anybody here actually use Kubernetes in production? Okay, so a few people. This command looks pretty familiar, but if somebody asked you to figure out all of the containers running in production, if you know kube control, this is basically what you would do. You could take a look at your deployments. This is manual right now. You'd obviously want to automate this or at least document it so you're not scrambling to figure this type of thing out during an incident. But, I ran this kube control get deployment command. This is the deployment that Jenkins X set up for me. Scroll down through all of the output and you can see the image name here. Does anybody see the problem with this? So there's a few problems, but one of them is that little piece on the right, :0.0.1. This image was deployed by a tag, and tags in the Docker universe are completely mutable. And so when Kubernetes schedules this, the pod, or the set of pods for this deployment, that's going to get resolved to an actual image at that time. You could have 10 copies of this running in your cluster that are all completely different bits of code. If anybody gets access to your registry or one of your developers forgets and overwrites the wrong tag, you're going to have different instances of this application running, and you don't know what's inside of them. That's both a problem for security and just production stability. And the incident reports just kind of write themselves when you think about this. So the first step when trying to adjust this pipeline is to make everything deploy by digest instead. With the Docker image, instead of the colon tag, you can do an @ sign and then reference these by their SHA. That means even if it changes or disappears, you're always going to get the same image. If it's gone, then you'll get an error rather than having some kind of unknown behavior in different versions of your application running. So I took the overall pipeline set up by Jenkins. This is a Jenkins file, for anybody who's familiar with this, and had to reorganize it a little bit. There are a few small changes to make JenkinsX deploy everything here by digest. Right here, installing a basic dependency that helps do the tag to digest resolution and then reordering things a little bit to make sure that I'm generating these configurations after the image has been built. Otherwise, there's no way to know it's digest. There were a couple more files I had to change, but overall, this is a pretty easy fix. In here is the make file. I'm using a Go app, and Go apps use make files as their build systems. If you're using something like NPM or Java, you're going to use a more language idiomatic system here. But this is basically just to grab that digest from the image we just built and then do some sed magic to stick that into the chart that we're going to deploy. Then the final piece. One of the ways to deploy applications to Kubernetes is using Helm charts, which I just kind of mentioned before. Helm charts are basically Go templating on top of YAML, so that way you can abstract away some of the parameters and values inside of the YAML. This right here gets executed against a set of variables that we use sed to spit out in that previous step. So this is switching the format to deploy from that version tag to a digest. And then voila, we push this change, JenkinsX automatically deploys it, and then we can check our deployments, and now this is referenced by SHA. So from here, we're sure that every single instance so every single pod running inside of that deployment will always have that same container. We don't have to worry about them changing or having different copies of the application running inside of the cluster. So the next step here, what packages are in those containers? If we can't figure out what containers are running, then it's not really useful to figure out what packages are inside of them. But now that we figured that part out, we're going to move on to the next step. So the use case here is something like shell shock or heartbleed hit, and you quickly need to figure out exactly what versions of the vulnerable packages are running and where inside of your cluster. JenkinsX provides some automation to help here, but it's not quite as easy as it could be out of the box. Those image names I showed before, these have that kind of IP address in front of it, and then some names. That IP address is private to the Kubernetes cluster by default with JenkinsX. They package a container registry with the deployment. You can run some kind of proxy or SSH into the cluster to get access to it, but then you're poking holes in the firewall, and it's making it harder than it needs to be. It also makes it a little bit more difficult to set up third-party services that automate a lot of this. So the next step in trying to set up this whole pipeline was to switch that in-cluster registry to a real production one that's running outside of the cluster. You kind of see a pretty small set of changes here. Setting up some environment variables so JenkinsX knows where to push things. To actually orchestrate the build and push of images, JenkinsX wraps this tool called Scaffold. It's an open source project from my team at Google. But, that config at the bottom is telling Scaffold what to name and how to tag the image and where to push it to. So instead of using an in-cluster registry, we're just going to use GCR. There are a bunch of registry options out there, depending on what cloud you're in. Some of them are more integrated and easier to set up. To make this change a little bit easier from a permissions perspective, I added another line here, which switches the build process to use Google Cloud Build rather than building inside of the cluster as well. That does introduce another dependency, but it has some security benefits that I'll talk about more in a little bit. So now that we've pushed this image, we can to a real registry, we can grab that on our laptop running Docker, pull the image down, crack it open and see what's inside of it. If you're using a Debian or Ubuntu-based system, there are a couple different commands to get a full list of all the versions inside of your package. You could always save it as a tarball and look at individual files as well. That works most of the time, but like I mentioned before, there's a bunch of awesome third-party tools to help automate the scanning and notifications of things inside of your image. There are a few open source projects like Grafeas, and Twistlock has some products as well to do all of this, the container vulnerability scanning. This is what the UI looks like inside of the Google Cloud Container Analysis API. Most Debian images have a bunch of out-of-date packages inside of them already, and you can kind of see the exact CVEs, their scores, and how important they are. Then you can decide if they actually affect your code and how quickly you need to get a patch out. So the final step here in the chain of trust is going from packages to the actual sources used to build them. Not all bugs, especially security ones, are caused by your dependencies. Sometimes you or your developers or your team makes mistakes too. If you notice a bug after it's been rolled out, you need a way to quickly find out exactly how exposed you are, where that bug made it to, so you can figure out where the fix needs to be applied. And this is where some of the GitOps pipelines start to shine. Since all of these events are triggered by events to Git repositories, you can start to grep through all of the logs and figure out exactly which container image was built from which Git commit. This works, and you can scrape and grep through a bunch of text files, but a lot of times you're trying to answer this question in reverse. So from each container image, which sources went into it, rather than the other way. You could always invert that map just by running a whole bunch of bash scripts, but there are a bunch of third-party tools and systems as well that automate this and start storing that metadata. This problem also starts to get a little bit recursive and can kind of drive you crazy if you spend too much time thinking about it. But it's not just about the packages that you built from source. You also have to start to consider which tools were used to build those. If you have a full chain of trust for your source code, but you're grabbing some random dependency from GitHub on the internet to actually do the build, again, that chain is only as strong as its weakest link. You can keep going around and around in circles here. At some point, you're going to have to trust some of your dependencies. How many times around this circle you want to go is up to you and your organization. Making it easier, though, allows you to get a higher level of security without going too crazy. So before I mentioned that other little change to use Google Cloud Build rather than building inside of my cluster, one of the benefits of using third-party build systems like this is that they store a lot of this information in a queryable and auditable way. Google Cloud Build is one option. There are a few other third-party services that do this as well. The APIs all tend to look the same. You give them some sort of inputs. It can be a pointer to a Git repository or some kind of tarball that you store by digest. They do the build, and then they store the output in some way you can go and query later. This is what the UI looks like inside of Google. They're all roughly the same. This was a simple build that just executed Docker to do a Docker build of a Docker file, but you can see that we have the exact hash digest of the input tarball, and then we know the exact digest of the image that came out of this. So I call this one the hierarchy of security needs. Up until now, we've kind of been focusing on this bottom one of if something bad happened and we happen to find out about it, we want to be able to figure out how bad it really was. If somebody stole customer data or changed a bunch of production systems, it's good to know that rather than not know. We're going to start moving up to the next two in the rest of this talk. Once we know how bad things were, it's good to start figuring out how to get notified earlier when things are happening to make that less bad. And then finally, you can start to look at some systems that stop bad things from happening, prevention. In security and in container security, there are a bunch of things in this middle tier about notifications. For container runtime security, there are a bunch of systems that analyze patterns inside of syscalls, network traffic to try to figure out if you're mining bitcoins or sending spam emails. But from a CI/CD perspective, this is really about just kind of knowing what's inside of your images and when problems are found with those dependencies. So that's where two open source tools from Google with these awesome logos come in. Grafeas is an open source metadata store for containers. So it supports arbitrary metadata storage that's all keyed back to a container digest, which is why it's so important to always deploy things by their digests. Some examples of things you might store inside of Grafeas are package information, vulnerability information, build history, things like who built the image and exactly which sources it came from. Grafeas just stores this information though. It doesn't do anything with it. It's up for to other systems to enforce policies based on that, which is where the Kritis project comes in. Kritis extends Kubernetes with a set of policies based on the information inside of Grafeas. So you can write policies that say things like, don't allow images inside of my cluster that weren't built in my environment, or only allow images to reach production that have been signed off by my QA team. That kind of structured policy information. Kritis uses a set of Kubernetes CRDs to define these policies, and I'll explain what those are in a minute. And it supports both auditing and enforcement-based flows. So for auditing, Kritis won't actually take any action to prevent things, but it will store information you can query on later if things are out of policy. And then the enforcement flow is actually active and will prevent pods from being scheduled that don't meet the policies you defined earlier. Finally, to establish that trust, it uses a series of PGP-based signatures called attestations, which are again stored back inside of the Grafeas library. I mentioned CRDs before. They're a pretty new Kubernetes feature, which there's a lot of confusion about. It stands for Custom Resource Definition, and this here is the way I like to think about them. They're basically a way of extending the Kubernetes API model with your own types. Kubernetes doesn't actually know or do anything with these types. It just stores them next to the other first-class types like pods and deployments, replica sets, and that kind of thing. You can write anything as a CRD. It's up to you to write something that actually does something with that data, though. Kubernetes just lets you, create them as YAML files and upload them with kube control. This is what the Kritis CRD looks like. It supports a couple different policies. At the top, we've got a basic whitelist for images. If you have some images that you know are going to be out of policy for some reason, but you don't care about them, you add those here. And then there are a couple different types of policies below. One of these, the one I have outlined here, is package vulnerability policy. So this is basically saying, don't allow me to run anything in my cluster that has vulnerabilities that are above that are at or above the high threshold. Like I said before, security isn't a Boolean, it's a spectrum. There's usually a couple dozen low to medium vulnerabilities any given day, and you probably don't want to be rebuilding and redeploying for every single one of those. But things that are up in like the high and critical threshold are a lot more important. And then finally below that, there's a whitelist for CVEs. Some of these don't apply to your code for some reason or don't really matter in your use case. So you can add things here so you're not constantly getting annoyed by them. Kritis works with two basic control loops. Like I said before, everything in Kubernetes is a control loop. One of these is about applying these signatures. So the first one is the signing policy control loop. Kritis is constantly looking at images inside of the registry, making sure that the metadata for those is scanned and inside of the Grafeas API, and then comparing that to the policies around what images it should sign. And those are called attestations again. So if it finds a new image in the registry that meets the policy for something that should be signed, it'll create that signature and store that back in the other store. Then finally, there's the admission policy loop. Kubernetes has a couple different extension points for the life cycle of applications. This one gets called every single time a new pod gets scheduled. So when a pod gets scheduled, that's when the container image might change running inside of your cluster. So every time that happens, Kubernetes consults Kritis to see if that pod should be allowed to run or not. Kritis cracks open the pod specification, looks for all the images inside, and checks to see if they meet all of the policies to be admitted. It stores those decisions and then just keeps running in this reconciliation loop. Yeah, so I'm going to show a little demo here. This demo involves trying to run known vulnerabilities in my cluster. Don't run this at home is probably a little bit of an exaggeration. It's not that bad, but definitely don't do this in production. So to get Kritis hooked up and working with JenkinsX, here's the exact CRD I had to use. I mentioned before that we have that image whitelist. Here's a case where I had to use it. JenkinsX comes with this little expose controller job that it runs every single time you try to deploy a new version of your code, and that didn't quite meet the policies that I'd set up. So I couldn't even get to the point to run my own code without that one. And I've applied this, all these policies are applied at the Kubernetes namespace level, which is how JenkinsX sets up environments. So I'm using the JX staging namespace to represent my staging environment. If you don't care about staging, you could apply this right to production, but it's normally better to catch these things early on before your production deployment is in progress. So here's the bad base image. I took from Scratch, which is what I had before. Scratch in Dockerfile land means no base image. Go apps are statically compiled, so they don't actually need any dependencies. But I switched this to a very old version of Ubuntu 18 that had some critical issues that I already knew about and patched. It takes around 5 or 6 minutes to actually get through this whole flow, so I'm not going to do it live here, but this is what the pipeline starts to look like. The app gets built, the container image gets packaged, the nice blue ocean UI shows that the release has all been built, and then you get to the promote to environment stage, where it tries to get deployed to staging. You can watch the staging roll out like this. Kubectl get staging, or get deployment inside of the staging repo. And as you can see, the deployment actually does get created. It will just never let the pod get scheduled. So the deployment is in this state where one instance is desired, but will always stay at 0 for current. Kubernetes will not allow those pods to ever run because the containers have vulnerabilities inside of them. If you inspect that deployment, you can see the status message at the bottom. The admission webhook for Kritis denied the request because it found violations in that image, which is again referenced by digest. So the overall recommendations I've talked about for this to start to secure the JenkinsX pipelines are always deploy everything by digest. This isn't really specific to JenkinsX, but it doesn't do that by default. So it's a pretty important change to make. If you don't do that, then you have no idea what's running and none of the rest matters. After that, it's important to know what's inside of your containers. So you have to tweak the JenkinsX configurations a little bit to make it easy to hook up scanning and access those images from outside of your cluster. Using a trusted builder makes it easy to store and analyze the inputs and outputs of those builds later. By default, JenkinsX runs those builds in your cluster, which kind of creates a cycle in your chain of trust. If you can't trust what's running in the cluster, then you don't know that those builds were done with the right steps that you asked for, and you don't know what's in those containers. And then finally, if you want to actually start enforcing policy, then you have all the data you need to use a tool like Kritis or something else to enforce policies based on all that metadata you've been so careful about tracking. Some of the other low-hanging fruit in this process are mostly around tying all this back to people and individuals. Anytime people and teams are at play here, you have to apply the same trust to them. So Git and GitHub and all these systems have a bunch of options for securing themselves, which JenkinsX doesn't set up by default. Things like requiring signed commits, locking down branches so people can't force push become very important here. They're normal best practices for developing on a team, but when that repo is directly hooked up to your production environment, it becomes a security concern. Build policies as well. Only allow containers to be built using certain tools. Mentioned before that if you're grabbing something random off the internet and using that to do the compilation, you are now trusting that thing you grabbed off the internet to not change. And Docker files, unfortunately, make this very easy to do inside of them. There's a bunch of Docker files. I was trying to get some stats, but couldn't find them in time, with the line inside of them like run, curl, pipe to bash. So now your whole build system and deployment system is trusting that web page on the other end. And then finally, Kubernetes has a bunch of runtime security mechanisms called pod security policies, which start to become important as well. If you're building or running builds inside of your cluster as root, you can start looking at policies to lock that down and not allow jobs running as root or with extra privileges. Cool. So that's all I had for today. Does anybody have any questions? Sure, over there. Yeah, so the question was about the recommendation to use digest instead of tags and the possible usability problem it creates because glancing at a tag gives you some kind of semantic information. Yeah, that is a huge concern. I actually just found this out recently, but the Docker spec actually allows you to put both a tag and a digest in there. And I almost changed the slide to include that. But you do something like :v0.0.1 to keep that semantic metadata and then also reference it by tag. And then if the tag and digest don't match anymore, you get an error. Yeah, that's definitely a good way to preserve the semantic metadata of which branch or which tag it was built from and keep the digest.
source tools that might help me audit the components in my infrastructure to be sure to find those vulnerabilities?
Yeah, so I mentioned Google Cloud Build. That's one. It's unfortunately not open source. There are a few other. Not sure. There are a few others that I'm not sure if they're open source. Azure has code pipelines. AWS has some kind of equivalent there. Another tool my team works on is called Canico, which is a way of doing builds inside of a cluster without using elevated permissions, like Docker would require. But Canico, K-A-N-I-K-O, but it doesn't have any auditing or policies built into it. Yeah, so I'm not aware of anything open source focused on build policies. So that recommendation was for Quay or Key. I'm not quite sure how to pronounce that, but it's QUAY.io. They're a container registry, and they have some of these tools built in as well. Over there? Have I looked at in toto? No, not personally. I know there's some integration work happening with Grafeas and in toto, though. Do you want to say a little more about it?
Yeah, my understanding was it helps you do the verification post-fact. Meaning it kind of it's like it's a control plane on top of your pipeline if you're able to express how you went through the entire supply chain. Right? Okay. Think of Jenkins pipeline as a supply chain. Kind of validates each step of the way.
Okay, cool. Yeah, I'll check that out. He explained it as a tool that kind of validates the overall supply chain, which you can think of as one Jenkins pipeline. Right there. Yeah, the question was about where the metadata is actually stored in Grafeas. Grafeas is both an open source API for how to store and query that data, and then there's an implementation of it as well. So that implementation runs a Postgres database inside of your cluster to store that metadata. There are hosted options as well that speak that same API. So for this demo, I was actually using the hosted one just to avoid having to set up Postgres myself. Did that answer the question? Yeah, so there are a bunch of tools that speak that Grafeas API and support publishing and consuming that metadata. For the CVE data itself, it usually comes from an open source tool called Claire, which is a tool for kind of taking Debian packages and Red Hat packages and joining that with vulnerability feeds. The APIs themselves are marked as beta because we keep adding new policies to it as well. But it's published as an open source release, so you can grab it and try it out. All right, thanks everybody for coming.